This is the title of the quiz question. I'm going to help you understand what it's asking. This sets up the problem. We are using a specific tool, PolynomialCountSketch, from the SCIKITLEARN library to speed up calculations. We need to figure out which statements accurately describe its workings. The PolynomialCountSketch helps us approximate a polynomial kernel. This is a fancy way to compute the similarity between data points. Imagine this like trying to determine how similar images are, and we're using this method for a fast way to find out. We have data, represented as x, and want to approximate it with a polynomial. This statement claims that PolynomialCountSketch directly calculates all the possible combinations of polynomial features. We need to check if this is accurate based on the algorithm itself. Here, we are testing whether the PolynomialCountSketch technique reduces the complexity of the data. It uses a clever technique known as random projections. I like to think of it as taking a quick snapshot rather than scanning every detail. This statement links the degree of the polynomial, specified by the degree parameter, to the number of random projections, which is wrong. The number of projections is determined by a different parameter, an underscore components. Statement D is about the trade-off between accuracy and computational cost when we change the an underscore components parameter. Increasing this leads to better approximation but takes more computing power and time. The sweet spot is where accuracy is sufficiently improved but the calculation remains manageable. This simply refers to the dataset containing the features used in the machine learning model. Our features are represented by x. That's it. I see that PolynomialCountSketch uses random projections. That's a clever technique to shrink the size of your data while keeping the important stuff. Imagine you have a huge pile of Lego bricks. Random projections are like randomly grabbing handfuls. You lose some detail, but you get a smaller, manageable representation of the whole pile. It's a key part of how PolynomialCountSketch works. The goal of random projections is to map the data into a lower dimensional space. It's like taking a 3D object and squashing it into a 2D image. You lose some information, but you make it much easier to process. That's precisely what PolynomialCountSketch does. It converts high-dimensional data into a lower-dimensional form, making calculations faster. Think of it as a handy data diet. Scikit-learn is a popular Python library for machine learning. PolynomialCountSketch is a specific function within it designed to approximate something called a polynomial kernel. We use this to speed up our machine learning algorithms without losing too much accuracy. It is a cool and fast way of handling your data. The dataset X represents the features of your data. Think of these as the characteristics or attributes that define each data point. For example, if we're trying to predict house prices, X might include the size of the house, the number of bedrooms, and the location. PolynomialCountSketch works directly with these features to create a faster approximation of the kernel. I'm talking about a specific function, PolynomialCountSketch, from a Python library called scikit-learn. It's used for a technique called kernel approximation, which is a way to make machine learning calculations faster. This is the core question. We'll look at several statements about PolynomialCountSketch, and I will determine which ones are correct. This statement says PolynomialCountSketch calculates every single feature of a polynomial kernel. This is incorrect. PolynomialCountSketch uses a shortcut. It doesn't calculate all those features directly. This statement is correct. PolynomialCountSketch uses a clever trick called random projections to reduce the number of features while still getting a good approximation of the result. Here's another false statement. The degree parameter sets the complexity of the polynomial, not the number of random projections. That's controlled by another parameter called an underscore components. This is absolutely true. The an underscore components parameter dictates the number of random projections. More projections generally improve the approximation, but they also make the calculations take longer. This simply means we have some data, called X, which has various features that we are using as input to our model. This is our main tool. It's a function from the scikit-learn library that is used for kernel approximation. It helps us improve the speed of the process. We're not calculating the actual kernel directly. We're using PolynomialCountSketch to make a good estimation, an approximation, of the kernel, which speeds up the computation. I'm using PolynomialCountSketch, a scikit-learn tool, to speed up my machine learning model by approximating a polynomial kernel. It's a clever way to handle high-dimensional data more efficiently. This question tests my understanding of how PolynomialCountSketch works and what its settings do. I need to decide which statements accurately describe the algorithm and the effects of its hyperparameters. Let's get to it. This statement is false. PolynomialCountSketch doesn't explicitly compute every single polynomial feature. Instead, it cleverly uses a shortcut to approximate the result. Think of it as estimating the answer rather than calculating it precisely. This is true. PolynomialCountSketch uses random projections, a mathematical trick to lower the number of dimensions in the data, making calculations much faster. It's like summarizing a really long story into a short, impactful paragraph. This is false. The degree parameter sets the degree of the polynomial kernel. The number of random projections is controlled by a different setting, an underscore components. I'm mixing up settings there. This is true. Increasing in underscore components means I'm using more random projections. This gives a more accurate approximation, but it takes longer to compute. It's a trade-off between accuracy and speed, a common issue in machine learning. This represents the data I'm using, the input features for my model. This is the type of kernel I want to use in my model. It's a polynomial kernel of degree 2. Meaning it involves squared terms. This is what PolynomialCountSketch gives me. A faster-to-compute approximation of the actual polynomial kernel. This question tests your understanding of how PolynomialCountSketch works in the scikit-learn library. I'll help you evaluate each statement to determine if it accurately describes this algorithm. This statement is true. PolynomialCountSketch cleverly uses random projections as a dimensionality reduction technique. Think of it like summarizing a long story. You keep the most important information while throwing out less important details. Random projections help PolynomialCountSketch achieve this efficient summarization of your data. This is false. The degree parameter sets the degree of the polynomial kernel, not the number of random projections. The number of random projections is actually controlled by another parameter called n_components . Think of degree as describing the complexity of the relationship between your data points, whereas n_components sets the level of simplification used in approximating the relationship. This statement is true. By increasing n_components which represents the number of random projections, you allow for a more detailed approximation of the polynomial kernel. The trade-off, however, is that you are doing more work, leading to higher computational cost. It's like having more workers to build a house. It will be done faster and more accurately, but at a greater expense. This is false. PolynomialCountSketch does not explicitly calculate all features. That would be extremely computationally expensive. Instead, it utilizes random projections to efficiently create a lower dimensional approximation. PolynomialCountSketch is a technique within the scikit-learn machine learning library, specifically designed for efficiently approximating polynomial kernels in higher dimensional feature spaces. Polynomial kernels are powerful tools, but can be computationally costly to work with in higher dimensions. This is what makes PolynomialCountSketch so helpful. This simply indicates that we have data, features, represented by the variable x. These features will be input into our PolynomialCountSketch algorithm. This specifies that we want to approximate a polynomial kernel of degree 2. The degree parameter determines the complexity of the polynomial relationships that we are trying to model. A degree 2 polynomial kernel models quadratic relationships between data points. This reminds us that PolynomialCountSketch provides an approximation, not an exact computation, of a polynomial kernel, achieving speed improvement at a potential cost to accuracy. This approximation is crucial for dealing with large data sets or high-dimensional spaces where a precise calculation of all features is impractical. This is a multiple-choice question about PolynomialCountSketch, ASCIKITLEARN tool for efficiently approximating polynomial kernels. I'll need to carefully consider how it works to select the correct answers. This question asks me to identify which statements correctly describe PolynomialCountSketch and its behavior. I need to understand the core function of this algorithm, specifically the way it handles the dimensionality and the degree of the polynomial. This refers to the input data, the features that PolynomialCountSketch will work on. Think of it as the data I feed to the algorithm for processing. This is the specific SCIKITLEARN function that I am focusing on. It's a method for approximating polynomial kernels, which helps speed up calculations in machine learning. This is a parameter that controls the number of random projections used by the algorithm. More projections mean a more accurate approximation but more computational cost. Think of these as the number of different ways I'm looking at my data to get an overall idea. This parameter specifies the degree of the polynomial kernel I'm approximating. A higher degree means the model can capture more complex relationships, but again, increases the computational demands. This basically describes the complexity of the relationships I'm trying to model in my data. This is the output, the lower dimensional representation of the original polynomial kernel features produced by the algorithm. Essentially, this is a simplified version of the features that are easier and faster to work with. This is the overall topic. I'm tackling a problem that involves approximating a polynomial kernel using a specific technique within SCIKITLEARN. This means I'm trading some accuracy for efficiency. This statement suggests that the algorithm calculates every single feature of the polynomial kernel. But that's incorrect. PolynomialCountSketch is designed to be efficient and doesn't compute all features explicitly. It uses a more clever shortcut. This statement highlights the core functionality of the algorithm. It reduces complexity by projecting data into a lower dimensional space using randomness. This is a key aspect of how it achieves computational speedups. Here, the question mixes up two distinct parameters: degree and n_components . The degree controls the complexity of the kernel, while n_components manages the number of random projections. This statement accurately reflects the trade-off inherent in using random projections. More projections, higher n_components lead to a better approximation but require more computing resources. It's a classic example of a bias-variance trade-off.